Swayam Prabha. Digital India. Educated India.
So far we have covered various integral conservation equations of mass, momentum. We have looked at certain considerations for the conservation of energy, and we have looked at non-inertial frames and all those things. But in this particular lecture, we're going to look at the differential equations which we can use to find out all the different variables in the problem. Okay, so let us start with the conservation of mass. So for a control volume which moves identically with the velocity of the fluid, the differential equation is integral, or rather the integral equation is, so this is integrated over the area, this is integrated over the volume. So now we can make use of the divergence theorem and write down the second area integral as a divergence. So this becomes integral del T of rho dV over the volume plus the divergence of rho u dV is equal to 0. So then we have integral of del T rho plus divergence of rho u, this entire object integrated over the volume equal to 0. And if this statement is to be true for any arbitrary control volume, then the integrand must be 0, which implies that for a differential element inside the control volume, we can shrink the control volume to whatever you want. You can shrink it to a point. So at a given point in the flow, this is the governing equation for the conservation of mass. We have seen the different kinds of simplifications that can happen, and the simplest point is when rho equal to constant, right? Simply boils down to the divergence of velocity equal to 0. And we have also seen the situation where rho can be variable, yet we can have del rho del T plus, so if we operate this divergence operator on this, it will be u dot nabla of rho plus rho times the divergence of u equal to 0, and this entire thing becomes the total derivative of the density plus rho times this equal to 0. So we can have a flow in which the density changes in time and space such that this total derivative can vanish. If that vanishes, then it's called as variable density compressible flow. But for whatever we are going to study in this syllabus, it is sufficient to employ this as the starting point. It says that the velocity is divergence free. Coming to the conservation of momentum, again let us write down the statement of the conservation of momentum for a control volume which moves with the fluid. So del T of rho u dV plus integral of rho u dot n dA is equal to summation of forces, and the forces can be categorized as the surface force, which is represented by means of a traction vector, plus a body force which is represented by means of an acceleration. And the common body force that most of the flows experience is the body force of gravity, the acceleration due to gravity. And all this is written in an inertial frame. That should be clear by now. Now once again we can convert this particular term, which is an area integral, and write it in terms of a divergence. Recall that this is the momentum content and this is the flux of the flow. So this has three components, but this is a single scalar. So we can use the divergence theorem and write this down, this particular term, as the divergence of rho u dV. So on the left hand side we have del T of rho u, dv plus this, and so the left hand side boils down to integral of del t of rho u plus the divergence of rho u, this entire entity integrated over the volume. On the right hand side we have the integration of this body force over the entire volume plus the traction force. Now let us recall from our considerations of equilibrium that the traction force at a point can be represented in terms of the state of stress at that point, and depending on the orientation of the area on which the traction force is acting, the force was given as tau dot n. Alright, so this particular term is equivalent to writing plus integral tau dot n dA. So the right hand side becomes integral rho g dv plus, we can make use of the divergence theorem to write this area integral in the form of a divergence, but in this case the divergence will be of the stress tensor. So finally, if this is also true and this is also true, we can write down this entire expression in terms of a single volume integral. So it will be del t of rho u plus the divergence of rho u minus rho g minus divergence of stress tensor integrated over the volume to be equal to 0. And if this particular integration is to be 0 for any control volume, the integrand must be 0, which implies that at a point the statement of the conservation of momentum boils down to this particular expression. Now let us look at how you can write down the different components of this equation. So let us write down the equation in the ith direction, or the, let us write it down in the jth direction. So the first term will be del t of rho uj, that is, it is the jth component of velocity, plus the divergence of, so because we are using an index notation, the divergence will become del xi rho uj ui. So the fact that u dot n cap gave rise to this divergence is captured in this repeated index I. But this j is not a repeated index, it is a fixed index. This will be equal to rho g j plus del xi of tau ij. So this is the Gurney equation. So this is the temporal term, this is the advective term, this is the body force term, this is the surface force term. Alright. So let us simplify this further in the jth direction. If this is true, then we can split the first term as del rho del t uj plus rho del uj del t. The second term can be written as plus rho uj del ui del xi plus ui del xi of rho uj. This is equal to the rho gj plus del xi of tau ij. These two terms are nothing but rho del uj del uj del t plus uj. Rather than splitting it like this, it is beneficial to rather split it in terms of this. So it will be rho uj del ui del xj plus ui. This is just for algebraic convenience. Okay, so when I take these two terms common, it will become, what is the term, ui. There is only a certain way in which you get the best benefit out of this splitting. Let me just rewrite this. So the second term can be split as rho ui del xi of uj plus uj del xi of rho ui. Yeah, that's it. This is equal to rho gj plus del xi of tau ij. Now we can combine these two terms and write rho del uj del xt plus ui del uj del xi. We can combine these two terms and write down plus uj del rho by del t plus del xi of rho ui, while the right hand side is the same thing, it's rho gj plus del xi of tau ij. Now this particular term is the total derivative of the velocity, so this is rho duj dt. So when you expand the total derivative term, you will obtain all these terms. Now this particular term is uj multiplied by the total derivative of the density. We recall that the total derivative of any variable is del phi del t plus ui del xi of phi. So using this definition of the total derivative, you can simplify these two terms as this. Now this particular term is 0 by the conservation of mass, and so the left hand side boils down to rho duj dt is equal to rho gj plus del xi of tau ij. This particular equation is called as the Cauchy momentum equation, and it was first derived by the famous mathematician Cauchy. So what this equation says is the acceleration of the fluid element is due to the body force and the divergence of the stress, but still we do not know what are the expression for the stresses, and that particular description of the stress tensor is falling under the categorization of the constitutive behavior. This particular equation is true for any continuum. This is not just restricted to liquids, it's equally valid for solids also. But where the distinction is the constitutive behavior. For solids, constitutive behavior is a relationship between stress and strain, whereas in liquids, the constitutive behavior is a relationship between stress and the rate of strain. All right. Before that, we should quickly bear in mind that tau ij is equal to tau ji, because the conservation of momentum for a differential element is supposed to be moment free, And we have already seen this at some point in our lecture. But this need not be the case for fluids which have a net couple acting on them. Now let us go towards the general description of a constitutive behavior. Let us consider a fluid at rest. For a fluid at rest, we know that the stress is isotropic and compressive. So if it is isotropic, compressive and equal from all sides at a point, so the stress must be written in the form of minus P delta Ij, where delta Ij is this. So delta Ij is an isotropic tensor. The negative sign accounts for the compressive, and minus P, which multiplies this identity matrix, is responsible for this equal from all sides. Okay, so all these properties of a stress tensor being isotropic, being compressive and equal, are embodied in this particular expression. So if tau ij is given as this, rather not if, but when the tau ij is written as this, it means that we are writing down the stress for a fluid element in equilibrium. For something which is at rest, right? Which means that P is also equivalent to the thermodynamic pressure. For a fluid which is in motion, obviously the fluid is no longer in thermodynamic equilibrium, and there will be some deviation from this particular form of stress. Alright, but before going into that, let us quickly look at what the divergence of this will be, this particular form. It will be del del xi minus P delta ij. This is minus comes outside, del del xi of P delta ij. Now the property of delta ij is such that it is equal to 1 when I equal to j, it is equal to 0 when I not equal to j. So this will be non-zero, rather it will be 1 only when I equal to j. So we set I equal to j and set this to be 1. So correspondingly, this particular I that exists over here will become del del xj of P. So it becomes minus del P del x, which means it is the gradient of pressure. So the contribution from the static component of pressure is manifested as the gradient of the pressure. And if a fluid is at rest, if the fluid is at rest, this entire left hand side becomes 0. And if that is true, we can write down the right hand side as, let us write down the three components. So 0 equal to rho. So let us write down the index equation, rho plus del del xi of tau ij, and this comes out to be rho gj minus del p del xj. So let us write it for j equal to 1. It becomes, so g1, that is the gravity acting in the x direction, is 0. 0 equal to minus del p del x. Then in the y direction, j equal to 2. 0 equal to minus del p del y. Now in the z direction, 0 equal to minus rho g minus del p del y. And the equation of motion reduces to the equation of hydrostatics. These two imply that P is not a function of x and y, it is only varying with z due to the gravitational body force acting on the fluid. So now that we have analyzed a fluid at rest, Let us proceed to analyze a fluid under motion. So fluid under motion the stress for a fluid under motion can be represented as this. The minus P delta Ej still remains from the static part and an additional sigma Ej. So this particular component is called as the static component. This component is called as the deviatoric component. So this is the deviatoric stress. Now the deviatoric stress, we have seen that it depends on the rate of strain. So sigma Ij is dependent somehow on the rate of strain tensor. And I'm not writing Ij because it can depend on other components of the rate of strain tensor also. And once again, because the fluid is under motion, P that we write over here, it is not exactly the equilibrium pressure, but it is in a certain approximation where the fluid relaxes very quickly. So what do you mean by relaxation? That given a disturbance from equilibrium, the fluid is able to reach equilibrium very quickly. That if you run a flight of steps, how fast can you sit down and calm down yourself so that a person who sees you can say, okay, he did not do anything, he is in equilibrium. If you are not in equilibrium, you will keep on panting for 5 minutes, but if you are in equilibrium, you will seem like you have not done anything. So if the fluid is able to reach equilibrium very quickly, this P can be approximated as the thermodynamic pressure or the equilibrium pressure. But the deviatoric stress is represented in terms of the rate of strain tensor, and a way to relate a tensor with another tensor is by means of a fourth order tensor. So a fourth order tensor is something which maps a second order tensor, in this case the rate of strain tensor, onto a stress tensor, much in the way like a vector can be mapped into another vector with the help of a second order tensor. Okay, so fourth order tensor mapping requires this. Now let us look at the different requirements of this relationship. Okay, so for this relationship to hold true, how many variables we must have? So I can go from 1 to 3, j can go from 1 to 3, m can go from 1 to 3, n can go from 1 to 3. Meaning sigma 11 is a function of s11, s12, s13, dot, 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 all the way to s33. So this relationship between all these terms in a linear fashion can be done by means of 81 constants. So sigma 12 will also be some function of this, sigma 13. Okay, so this relationship that we can write will involve 81 constants, but that's really cumbersome to do. So we must find out various underlying symmetries in the problem which can help us to simplify the expression for the stress tensor. So the first requirement is that the stress tensor must be isotropic. If the stress tensor is isotropic, then the fourth order tensor which maps this rate of strain tensor must also be isotropic, meaning Kij Mn must also be isotropic. And the only way to express a fourth order tensor through isotropic means is by using two Kronecker deltas, rather a pair of Kronecker deltas. Now the requirement of the tensor being symmetric means you can swap I and j and still obtain the same result. So ij should be swappable. So if it is swappable, it means that Kjimn will be lambda delta ji delta mn plus mu delta jm delta in plus gamma delta jn delta in. and because it is equal, so k jimn is also equal to k ijmn, and it is equal to this thing. Now ij are swappable for delta because I equal to j is all that matters for the Kronecker delta. So this will be delta ij delta mn. This mu from this equation and gamma from this equation, these two terms exactly match. Delta in, delta jm, delta jn also match. So these two terms are also equivalent. So I'm not going to write it down, but the condition of symmetric stress tensor implies that mu equal to gamma. Thus kijmn so far is lambda delta ij delta mn plus 2 mu delta im delta jn. So with this we can write down the deviatoric part of the stress tensor as kijmn smn. This is lambda delta ij delta mn smn plus 2 mu delta im delta jn smn. Now delta mn smn is going to be non-zero only when m equal to n. So this becomes smm, and this is simply 2 mu delta im delta jn smm. Now what is smm? SMM is S11 plus S12 plus S13, rather S22 plus S33, and this is nothing but the trace of the rate of strain tensor. And the trace of the rate of strain tensor, you may recall, is nothing but the divergence of the velocity field. Alright, in that case, we can write this as sigma ij is equal to lambda delta ij divergence of velocity plus 2 mu delta im delta jn smn. So the entire stress tensor may be written as minus p delta ij plus 2 mu delta im delta jn. In fact, let us simplify this delta im delta jm also. So only when m equal to I and only when n equal to j, this term will be non-zero. So this becomes, so replace m by I and n by j. So this becomes Sij. So already we are able to recover the kind of form that we are used to. This is 2 mu Sij. For unidirectional flow, this boils down to the Newton's law of viscosity. You should be able to verify that. Newton's law of viscosity for unidirectional flow. Now, when we set I equal to j in this expression, this becomes tau ii is equal to minus p delta ii. Now, delta ii is equal to delta 11 plus delta 22 plus delta 33. It is equal to 3. So, this becomes minus thrice pressure. This becomes minus 2 mu Sii plus this becomes again 3 lambda, the divergence of the velocity. Moreover, Sii once again is the trace of the rate of strain tensor, and this becomes minus 3p plus 2 mu plus 3 lambda times the divergence of the velocity. Now, divergence of velocity, the diagonal components need not be equal, unlike this. So we can simply take an average. Okay, we can simply take an average and define the mean pressure. Define the trace of the stress tensor as the mean pressure. So the mean pressure equal to trace divided by 3. Essentially, this is by definition. So this is equal to minus p is equal to tau ii, the trace of it divided by 3. Essentially, it's like taking an average of the diagonal components. So if this is true, we can write down this expression as minus 3p bar is equal to minus 3p plus 2 mu plus 3 lambda times the divergence of the velocity. And the reason I am writing it as 3p bar is to differentiate this pressure from this pressure. This is the thermodynamic pressure. While this is the mechanical pressure. It is the mechanical pressure because it is the trace of the stress tensor. Alright. So now in that case, we can finally write down P minus P bar. So let me take this over here. We can write it as 2 by 3 mu plus lambda times the divergence of the velocity. So the difference between the mechanical pressure and thermodynamic pressure is manifested by means of this particular coefficient, which is called as the bulk viscosity. And the bulk viscosity is a measure of the compressibility. So if the compressibility is equal to 0, that is the flow is incompressible, then the mechanical pressure and the thermodynamic pressure become equal. When the when the flow is compressible, this will not be equal to 0, and the deviation between the mechanical pressure and thermodynamic pressure will be manifested through the bulk viscosity multiplying the degree of compressibility of the flow. It is not the compressibility of the fluid, but it is rather the compressibility of the flow. The more the flow will be compressible, the more important this bulk viscosity will be in the calculations. And this is typically important for problems of acoustics, problems of compressible flows, shock flows, and so on. But for typical flows, if the flow is divergence free, the bulk viscosity does not come into the picture. The Stokes hypothesis says that 2 by 3 mu plus lambda is equal to 0, meaning the bulk viscosity is 0. And in fact, it is 0 for most monoatomic gases and all those things, but for polyatomic gases, this is actually non-zero. Because it is that microscopic detail of being polyatomic that imparts a certain compressiveness when the flow of such fluids does happen. So now, what have we inferred so far? We know that tau ij is minus p delta ij plus 2 mu sij plus lambda times the divergence of the velocity. We can substitute the pressure from the previous terms over here, but in fact in this particular course, because it's a basic level course, we're gonna consider incompressible flows. This term vanishes, in which case the stress tensor is going to be minus p delta ij plus 2 mu sij. This is the form of the stress tensor. Now when we take a divergence of this, essentially the right hand side of the Cauchy momentum equation, the first term will give minus del p del xj, while the second term will give del xi of 2 mu sij. So sij is half del uy del xj plus del uj del xi. So this becomes minus grad p, its j component, plus, so this 2 cancels out, so it's mu del 2 ui by del xi del xj plus mu del 2 uj by del xi 2. Now if we focus on this del 2 ui del xi del xj is nothing but del xj of the divergence of the velocity, and if the flow is incompressible, this again vanishes. So the divergence of the stress gives us the gradient of pressure, its j component, plus mu Laplacian of the j component of velocity. Essentially, rho d uj dt is equal to minus gradient of p, its j component, plus mu Laplacian of the j component of velocity plus rho gj. In a vector form, this may be written as rho du dt is equal to minus gradient of pressure plus mu Laplacian of u plus rho g vector. Now let us take a step forward and simplify this, because it's a Laplace operator and a velocity. We can make use of the vector identity that the curl of a vector is equal to the gradient of the divergence of the vector minus Laplacian of the vector. This is a vector identity. You can easily prove this using the index notation, and I request you to go ahead and prove this in your leisure time. It is a good exercise to do. Just remember that the curl of something epsilon ijk, so the I component of this curl will be epsilon ijk del xj ak. So you have to make use of this form, and everything else is self-explanatory. Using this, if the flow is incompressible, this vanishes. So this becomes equal to minus of the Laplacian of u. So this particular equation may be simplified as rho du dt is equal to minus gradient of pressure. So now using this identity, so curl of the velocity will be vorticity. So this term becomes minus mu curl of the vorticity plus rho g. And so essentially we have an equation in which the force is somehow dependent on the vorticity, but we have already discussed this in one of the earlier classes that the forces must not depend on the vorticity. But why does vorticity appear over here? In fact, it actually does not. The stress does not depend on the vorticity, it depends on the rate of strain, rate of deformation. But the reason why vorticity appears here is it is the curl of the vorticity. It is not the vorticity alone, but the way vorticity varies spatially that gives rise to viscous stresses. If vorticity is constant in the flow, meaning there is some sort of solid body rotation, then this term automatically vanishes. When viscosity is negligible, rather viscosity is absent. I mean, viscosity can never be absent. Speaking for common examples, of course, I'm not talking about superfluidity and all that. So when viscosity is zero, or when viscosity is neglected, then the equation boils down. The Cauchy equation becomes this in an inertial frame. This particular equation is called as the Euler equation. Now we can we could have derived this Euler equation from a different viewpoint also. We can derive the Euler equation from simple momentum conservation principles. Let us consider a streamline on which there is a fluid element. Let this direction be S, the streamwise direction, and this direction be N, the normal direction. So the acceleration, so we know that the fluid element will move along the streamline. So the velocity is always going to be along the direction ES as opposed to the direction EN. But the acceleration will have both components. So the acceleration in the S direction will be del V del T, where V is the magnitude of velocity in the ES direction. So the velocity vector for this kind of flow is simply VES. So it will be del V del T plus V del S of V. But what are the forces acting on the fluid element? It is the pressure at this point minus the pressure at this point. So it is P at some location S minus P at some location S plus dF times the area. So the area will be equal to, say, delta n. Let us say that the unit width, there is a unit width into the plane. So this times delta n. So what is it? It will be minus del P del S delta S times delta n. So this is the force in the S direction. What is the force due to gravity? The force due to gravity will be decomposed into the S direction and in the N direction. So let me extend the N direction like this. This is the direction of the velocity and this is the direction of the horizontal. This angle and this angle are the same. Alright. So the angle can be written as, so let us, before going into writing down the exact term for gravity, so mass times the acceleration of the object is equal to minus del P del S delta S delta N, and the force because of gravity is minus rho G, but it is acting in the Z direction, right? But the mass of the object is, rather the volume of the object is delta S delta N, and there will be another cosine of theta, right? There will be another, no, in this case, if this angle is theta, then this angle is also theta. Okay, so delta S times cos theta. Oh, rather it won't be cos theta, it will be sin theta. Because the projection of of this gravity force in the cos direction will be along the n direction, not the s direction. So the mass here will be rho times delta S times delta N times AS is equal to minus del P del S delta S delta N minus rho G delta S delta N times times sine of theta. Now the sine of theta will be equal to what? It will be equal to, so this particular height change divided by the, let me draw the element a bit clearly. Let this be the element, let this be the streamline direction, right? So we are bothered with this angle. So this angle is the same as this angle, and sine theta in this case will be equal to delta Z upon, what is the component of, still not clear. The acceleration due to gravity, how can we decompose the angle? Let's see. Okay, let us keep it like sine theta. Let us divide everything by delta S and delta N. So it becomes rho AS is equal to minus del P del S minus rho G sine of theta, where sine theta will be the rate of change of height of the streamline locally per increase in the streamwise coordinate. Okay, so sine theta in this case, it will be the rate of change of increase of height, or rather the increase of height per increment of the arc length. Okay, so it becomes rho AS is equal to minus del P del S minus rho G del Z del S. So this defines the Euler equation along the S direction. This encapsulates how the streamline looks, nothing else. Essentially, the component of the gravity along, this is nothing but accounting for the component of gravity along the streamline direction, instantaneous streamline direction. Similarly, for the n direction balance, so momentum balance in the n direction, it will be, so what are the acceleration terms? The acceleration term as seen from the inertial frame will only be v square by r, where r is the local curvature with respect to which the fluid element is moving. Okay, so it will be minus rho delta S delta N, the mass of the element, times v square upon r. This will be the force acting in, this will be equal to the force acting in the n direction. So the force at this point will be P at n, the force at this point will be P at n plus delta n. So it will be minus del P del n delta n delta S minus rho G. So now the other direction will be del Z del N. Instantaneously, let me just, okay, so instantaneously at this point, del Z del N gives us the sine of this theta, whereas del Z del S gives us the sine of this theta, that is how much Z varies with an increment in S, but how much N varies, how much Z varies with an increment in N, that will be equal to the cosine of this theta. It's simple geometry. Okay? So this particular thing is the cos of theta. So with this in mind, we can simplify this as rho v square upon r, where r is the local radius, is equal to del p del n plus rho g del z del n. So this is the Euler equation normal to the streamline. This is the Euler equation along the streamline. With the help of these equations, we can solve various problems of vorticity. I mean, you just need to find out all the various terms. Let us do a quick example. Let us consider a velocity field given by ax square I minus 2 axyj. So we have been given the velocity field in the Cartesian direction. Let us see whether this flow is divergence free. So del u del x is 2ax, del v del y is equal to minus 2ax. So when you add this two, you get 0. So the flow is divergence free. Now let us find out the acceleration component. So acceleration in the x direction is del u del x plus del u del t plus u del u del x plus v del u del y. This term is 0. So u is ax square, del u del x is 2ax, v is minus 2axy, del u del y is equal to 0. So this becomes 2a square x cube. Ay becomes u del v del x plus v del v del y. So this becomes ax square. So del v del x is minus 2ay plus v is minus 2axy del v del x, rather del v del y, which is minus 2ax. So this comes out to be minus 2a square x square y plus 4a square x square y. Let us in fact find everything out at the point x equal to 1 and y equal to 3. At x equal to 1, ax becomes 2a square and ay becomes equal to y. So this becomes what? This becomes essentially this is 2a square x square y. So substitute y equal to 3. So this becomes 6a square. So the acceleration at this particular point at any time would be given by this. Now we need to decompose this acceleration. Now we have essentially ax and ay as two components of the acceleration vector, but we need to decompose it along the direction of the velocity. We need to decompose it along the direction of velocity. So how do you do that? Let us find out the unit vector along the velocity at this point. So the velocity at that particular point will be, so set a equal to 1, so it will be ai minus 6 aj. So the normal vector, rather the tangential vector, the s vector, it will be the u vector divided by the magnitude of the u vector. So it is ai minus 6 aj divided by a times square root of 37. So the component of acceleration in the s direction will be the a vector dot es vector, essentially, which is 2a square I plus 6a square j dot ai. So the a cancels out, so the a cancels out, so it is I by square root 37 minus 6j upon square root 37. So this acceleration component along the s direction comes out to be 2a square by square root 37. So 36 minus 36a square upon square root 37. Now that we found the acceleration component along a streamline, we must now find out the component normal to the streamline, that is a dot en vector. Now for a streamline, this is the es vector and this is the en vector, and the easiest way to find out the unit vector orthogonal to es is to do the following. The en vector would be the k vector that is coming out of this page, cross product with ES. The ES vector we've already found out as this. So once you take a cross product with this, you get the EN direction. After having found out the EN direction, we can find out the AN component as well. So I'll let you do this particular bit of computation, it's rather easy. So once we have the AN component, we know that the AN component is going to be equal to minus v square by r, where v is the magnitude of the velocity and it is given as square root of 37 times a, and we know that it's in the ES direction. So with the help of this, we can find out the radius of curvature as minus v square upon the magnitude of the normal acceleration. So with this, we've covered aspects of the Euler equation in Cartesian coordinates and in curved coordinates. In fact, if you look at the appendix of any book, when you use a cylindrical polar coordinate system, you will find that this particular derivative, when you split, so for a cylindrical polar coordinate system, you have the velocity in the E theta coordinate and the E r coordinate. So when you do that, we do find the presence of the v square by r kind of terms, and these are born out of the fact that the streamlines are curved. So with this, we end this particular lecture, and I'll see you next time where we will study Bernoulli's equation. It's goodbye from me. Bye. So finally, in this lecture, we have looked at the differential form of the continuity equation, the momentum equation. We have looked at the various constitutive relationship ideas of isotropy and symmetricity, and how they lead to a simplification in the constitutive behavior. From this, we've seen what the bulk modulus, or rather the bulk viscosity is. From that, we moved on to the case where viscosity is treated to be zero, that is the Euler equation. We've derived the Euler equation in Cartesian coordinates, and we have derived it for the case of a curved streamline. The curved streamline also gives rise to the centripetal acceleration, in case you are quite observant. So with this, we conclude this particular session. Next class, we'll look at the Bernoulli equation. But before ending, I just want to say that the Euler equations are quite notorious to solve numerically because of the lack of diffusion. In fact, the presence of diffusion by means of momentum, rather the presence of viscosity, is something which gives a very stabilizing effect to various numerical algorithms used to solve CFD flows. Besides this, the paradigm of Euler flows is something which is not very unrealistic, but we have to look at regions where the approximations are valid. For example, the flow near the surface of a plate, that is affected by viscosity, but regions very far away from the plate are not so affected by viscosity. So that leads to an abstraction of the entire problem into two zones: a zone in which the viscosity is not quite effective, but a zone where the viscosity is effective. So in the zone which is away from the walls, we can sort of treat it as an Euler flow, whereas the region near the wall, we have to actually apply the full set of the momentum equation. So it's not just something to make life simpler that we neglect viscosity. It actually pops up in various cases, and we'll see in due course how in boundary layer theory that figures in our problem. So with this, it's goodbye from me. Have a nice day. Bye.